Welcome everybody to a lesson on IPv4 subnetting. I'm going to be going through everything you're going to need to know to be able to subnet IPv4. And we're going to start this evening with some basic math. So what are the powers of 2? And we've got 2 to the power 0 all the way up to 2 to the power 7. Sorry, a bit of a sneezy situation I'm in at the moment. I'm sure it will go off. I'm going to give you a moment to think about what the powers of 2 are, and then we'll go through them. Okay, so if you've paused the screen there, let's just write on what the powers of 2 are. Let's start with 2 to the power 1. 2 to the power 1 is just going to be 2. 2 squared, well that's 2 times 2, so that's going to be 4. 2 to the 3, well that's 2 times 2 times 2, that will give me 8. And 2 to the power 4, that's 16. 2 to the power 5, well that's 32. 2 to the 6, timesing this by 2 again, will give me 64. And 2 to the power 7 is 128. So I'll come back now to 2 to the power 0. If you remember your indices in GCSE, anything to the power 0 is equal to 1. So my answer here is 1. Okay. So you should have got those answers for what the powers of 2 are, and here are the proper slides with the answers: 1, 2, 4, 8, 16, 32, 64 and 128. So any number between 0 and 255 can be represented using the powers of 2. So 255 is 111, 111, 11. 0 is 0, 0, 0, 0, 0, 0, 0, 0, 0. 78 is 0, 1, 0, 0, 1, 1, 1, 0. 199 is 1, 1, 0, 0, 0, 1, 1, 1. These strings of binary numbers are known as octets. So we're going to be working with octets in subnetting this evening, but you first need to know how to convert the numbers into binary, which is what we're going to look at. So let's look at the last example on the previous slide, number 199, which is 11000111. I've got that number here. 199 is 11000111. And notice I've lined up the powers of 2 over and above the binary string. So we've got 2 to the power 0 at the far right and 2 to the power 7 at the far left. And notice that underneath certain numbers we've got 1s, and under others we've got 0s. So the idea is that these powers of 2 can be added together to generate the same number that we are looking for. So if I add 128 and 64 together, that's going to give me 12, carry a 1. 1 plus 2 is 3, plus 6 is 9, and 1 carried is 192. And then if I add 4 to 192, I'm going to get 196. If I add 2 to 196, I will get 198. And finally, if I add 1 to that, I will get the target number 199. So I've just proven that 199 can be written out in this form: 11000111. But how are you going to be able to do that? Well, that requires you to be able to add the two powers of 2 together. So I'm going to give you a second to consider the following set of slides. We've got 2 to the power 7 equals, 2 to the power 6 equals, 2 to the power 5, 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. So we're going to start by filling in what each of the 2 to the powers are. So 2 to the 7, that's 128, and 2 to the 6 is 64. Okay, 2 to the 5 is 32, 2 to the 4 is 16, 2 to the 3 is 8, 2 to the 2 is 4, 2 to the 1 is 2, 2 to the 0 is 1, and then I'm going to change colour and we're going to work these out. So 128 and 64 together gives me 192. So that's the first one to really be aware of, 192. That's what you're going to get if you add 64 and 128 together. If I put 192 above the 32 now, and I work out what I'm getting here, I will get 4, 2 and 2, 224. If I now add 224 and 16, that will give me 240. 240 plus 8 is 248. Two squared is 4. If I put the 248 at the top here, that will give me 252. If I add 2 to 252, I will get 254. And if I add 1 to 254, I will get 255. Which, as I mentioned before, is all ones. So 8 ones in a row is 255. So you'll see on the next slide, I've got all of those numbers written out for you. Duck my head down so you can see that. Or I can scroll it down perhaps. Yeah, there we go. You've got all of those together. But if you can bear in mind 192, 224, 240, 248, those are going to be very helpful in conversion of your subnets, or conversion of your numbers into binary. Okay. So let's have a look at an example. 186. 186 is less than 192. So there's going to be no 2 to the power 6 in this. So you will have 128 because 128 is less than 186. But I can't squeeze another 64 into 186. So the way I deal with this is to say, well, if I take 186 away from 92, I'm going to get 6. And if I take that 6 away from 64, which is 2 to the power 6, I'll get 58. So I know that 186 minus 128 is going to be 58. And then I have to consider, well, what does 58 consist of if I want to break that down into powers of 2? Well, I can break 58 into 32, add 16, add 8, add 2. 32 is 2 to the power 5, 16 is 2 to the power 4, 8 is 2 to the power 3, and 2 is 2 to the power 1. So I've completed the table here. 2 to the 7 is 1. We've got 1 in that column. 2 to the 6, we've got 0 in this column. 2 to the 5, we've got 1 here because there's a 32. 2 to the 4, we've got a 16 because there's 1 there. 2 to the 3, there's 1 of those because we've got an 8. We haven't got a 2 squared because there's no 4 in 58. So that goes down as a 0 in the binary. And 2 to the power 1 is 2, which gives us a 1 in this column. And finally, 2 to the power 0, which we should know is 1. There isn't a 1 in 58, so we're going to put that down as 0 here. Okay, so the binary representation of 186 is 101111010. Okay. I hope that made sense in terms of what you're doing there to convert the number into binary. Right. So, the next thing we have to look at is, can you do this? Can you convert 73 into its binary string, 137 and 238 into their binary strings? So I'm going to give you a couple of moments to do that, and we will come back and go through the answers. Right, so I will just scroll the page down to show you there is another number there. It's 238. So, a quick reminder, if you're struggling with this, 2 to the 7 is 128, 2 to the 6 is 64, 2 to the 5 is 32, 2 to the 4 is 16, 2 to the 3 is 8, 2 to the 4 is 4, 2 to the 1 is 2, and 2 to the 0 is 1. So you should be able to see immediately with 73 that I can't put 128 into 73. So that means there's going to be a 0 in the 2 to the 7 column. There is room for 64. So if I take away 64 from this, oh, that's a bit messy. I'm going to get 9. So I can put 1 in the 64 column. And then 9, well, 9 is just equal to 8 plus 1. So for the 8, which is 2 to the power 3, I can put a 1 in. And 2 to the power 0 is a 1. All the rest, they're going to get zeros. $137. So this can fit 128. I can take that away from 137. So I can put a 1 down in the 2 to the power 7 block. Now what are we going to get here if I take that from that? Well, if it was 138, I'd get 10, so it's 9 again. Okay. So as we know before, 9 is 8 plus 1. And in the 8 and the 1, we can put in a 0, put in a 1. And zeros fill up the rest. Lastly, we've got 238. So this requires me to do a little bit of mental arithmetic and to know that from the previous slide that 2 to the 6 plus 2 to the 7, do you remember, was equal to 192? Yeah? If I added on 2 to the 5, that was 32, I would get 224. And then if I added on 2 to the 4, which is 16, I would get 240. Now 240 is too high. But the first 3 powers of 2, 2 to the 7, 2 to the 6, and 2 to the 5, they're all going to be 1s because we can get 224 out of 238. If I subtract 224 from 238, I will get 14. And 14 is going to be equal to 8 plus 6, which is the same as 8 plus 4 plus 2. So 8 and 4 and 2, that's 2 to the power 3, 2 to the power 2, 2 to the power 1, and everything else is a 0. So that is how we convert these numbers into binary strings. On the next slide you will see that I've got the actual answers there in a much more neat manner, but I wanted you to have a go to see if you could do that, to go through the process of adding the 2 to the 6, 2 to the 7 together to make 192, add on another 2 to the 5 to make 224, and then seeing if I added another 16 it would be too much to get the 238 there that we needed. So it's helpful to know that, because it allows you to go very quickly to these higher numbers which sometimes come up in IP addresses. So again, there are the answers. I'd like you to have a go at those yourself. Let's move on. An IPv4 address consists of 4 octets. So we're not just doing the process like we did here once. We're going to be doing it 4 times to generate an IP address. And this is your opportunity to have a go and see if you can convert this IPv4 address into its binary string. I'll give you a few moments to do that. Welcome to the one viewer we have on the stream. I'm going to quickly nip back to this to grab this. And plonk this here. This will help. The table is off. Okay, so I'm going to go through this once I've finished constructing this table, and then we'll go from there. So the first one is 192. 192 equals 128 plus 64. We should know that from what we were doing on a couple of slides ago. So 192 is the first of the 4 numbers, and we will get 1 in the 2 to the power 7, column. Ooh. No, I want to copy this. Obviously it doesn't want to copy for me, so let's do it a different way. And then we're going to need 1 in the 2 to the 6, and then all the rest will be zeros, because we've hit the target number straight away there. Oh, no, we don't want ones. We want zeros. So the next number is 168. $168 is equal to 128 plus 40. Yes. And I'm going to put this up here. That means that we're going to get 1 in the 2 to the power 7 block. We will get a 0 in the 2 to the power 6. What about in 2 to the power 5? Well, 40 can be made up from 32 and 8. So 2 to the 5 is 32. We can put in a 1 here. 2 to the 4 is 16. Well, if we use the 32 up, there's only 8 left, so that's going to be a 0. 2 to the 3 is a 1, because that's 8. And then all the rest will be zeros, because I've made up the full amount for this column. Right, so 0 is the third octet. So 0 will be uniform throughout. Every single cell in the third octet will be 0. Rather brilliantly. No, I'm having difficulty here just typing them all in. Lastly, but by no means least, we have 123. So 123 is less than 128. Okay, so that means 2 to the power 7 will be 0. And I'm going to move this 123 here. 0 will go in the box here. And we now have to make up 123 out of the numbers that we know. So 64 plus 32 will make 96. So those are both going to be 1s. (96) plus 2 to the 4, which is 16. That will make 102. 112, so that's allowed. If I add another 8, that will make a 120. So I need to get 3 more. 2 to the 2 is 4, so that is not allowed because 4 is greater than 3. And 3 is made up from 2 plus 1, so I'm going to get 1 and 1 in the remaining cells. So I hope you are able to get that. If I move on to the next screen, we'll see the answer here. I'll duck my head down just a little bit, I'll scroll the page up. .101.000.000.000.0111111. Okay, so this should be your bread and butter, being able to convert a IP address into its binary equivalent. I'm going to go through a little bit of the classes now. So each and every IP address is separated into classes, and you'll find that the big classes are like the Class A. Those are the ones that are given to multinational corporations and big companies, and they will be between 0 and 126 in the first octet. In B, these are medium-sized organizations. 128 to 191 will be in the first octet for Class B. Class C classes will be 192 to 223, and D and E. D is used for multicast, and it's between 224 and 239 in the first octet, and E is between 240 and 255, and they're really reserved for special use. So I've included on the right hand side priority bits. So I've got 0, 10, 110, 1110 and 111. The way to think about those is that in your first octet, your binary address will always begin with those priority bits. So for any Class A address, it will always begin with a 0. For any Class B address, it will always begin in the first octet with 10. For a C address, it will always begin with a 110, and D is a 1110, and E 4 ones. So there's a couple of things I need to mention about these classes, and I'll do that on the next slide. 127 between Class A and Class B is used as a loopback address for testing, and 0 in Class A at the very start is typically reserved for Dynamic Host Configuration Protocol, DHCP. Okay, but you need to know what octets and what classes correspond with each other. So Class A will be 0 to 126, Class B 128 to 191, Class C 192 to 223, Class D 224 to 239, and Class E 240 to 255. So we're now getting into the subnetting part. Obviously, the most used addresses will be Class A, B, or C in the internet. They will be Class A, B, or C. Class D and E are not really used very much, which means that there's going to be a limited amount of space in these ranges. So the way they get around having limited space is to separate the address into a network address and a network address and a host address. I do apologise about that. So for a network address, all the host bits are going to be 0. For the broadcast address, all the host bits are going to be 1s. And a host address will be somewhere between the above two. So yeah, did I say that correctly? Just check ahead here. Yeah, you've got a network and a host portion of your of your IP address. So yeah, I was right. You've got a network portion of your address and a host portion of your address. But for the time being, if you can learn that network address, all host bits will be 0. Broadcast address, all host bits are going to be 1s, and host address will be somewhere between the above 2. Subnet masks. So these allow us to split or separate an IP address into a host portion and a network portion. So this is where we really get going with the subnetting. So for Class A, the mask will be 255.0.0.0, or it has a notation of /8. For B, it's 255.255.0.0, which is a /16. And C, it is 255.255.255.0/24. So if you think about this in terms of binary, remember each one of those octets has 8 binary numbers in it, and for a number to have a value of 255, every single number has got to be a 1 for every value of 255. So with Class A, /8 means that there's going to be 8 1s in the first octet. For Class B, there's going to be 16 1s in both the first and the second octet. And in Class C, there will be 24 1s in the first, second and third octets. Subnet masks can have different lengths. So for instance, a /28 tells you how many places in the 4 octets will be 1s. So as I said in the previous slide, /24, all of your first 3 octets will be 1s, and then there will be 4 more 1s in the 4th and final octet. And you can see here I've spelt out /8, /16 and /24, which are Class A, B and C subnet masks. You can see that there's a lot of 1s in the /8, 16 and /24. More so in the /24 than the others. So the 1s will be the network portion of your subnet mask, and the 0s will be the host portion of your subnet mask. But fear not if that didn't quite resonate with you. I'm going to do an example here. We can use the subnet mask to help us determine the network ID and the broadcast ID, and the range of the host network address can also be seen. So I've got an address here, 160.26.129.49/17. So the first thing you've got to do with this question is to convert that IP address into its binary equivalent. I'm going to go through how to do it, but if you want to take a moment to pause the video and do it yourself, I'll give you that grace to do that now. Okay, so it's the same process as I did before. 160 is going to be 1, 0 for the 64 because we're not getting up to 192. 128 plus 32 will make 160, and then it's going to be zeros for the rest. Dot 26. So it's going to be 3 zeros because we've not got 128, 64 or 32. We do have 16. We do have 8 because 16 plus 8 is 24. We don't have 4. We do have 2. We don't have 0. We don't have 1. 129, well that's going to be 1 for the 128. 6 zeros. And then 1 more because 128 plus 1 makes 129. And then 49, well, it's not going to be 128 or 64. but we will be able to get 32 out of that. So 49 subtract 32 gives me 17. 17 can be made from 16 and 1. And that is the network address there, converted. The mask, well, a /17 means I'm going to have 17 ones. 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. And 17, 4, 5, 6, 7. Dot 1, 2, 3, 4, 5, 6, 7, 8. Okay. So you should have been able to generate that. I'm going to shrink this down because it's not fitting on the screen very easily. Don't go off the edge for me. There we go. So that's your address. And that's your mask. There and there. You can see that there. On the next slide, I actually do the whole thing again, and I hope you got those values for your IP address and your mask. So how do we use that once we've got an IP and address and a mask as seen for the question? Well, the 11111111111.1, the /17 part, all the ones represent your network part of the address, and all the zeros of the subnet mask represent the host portion. So we're going to look for the network address. So to do that, everything in the same field as the mask will remain the same, i.e. the green section, everything will remain the same. Everything else, i.e. in the red section, will become 0. So I spell that out with this binary address at the bottom. 100.000.110.170.8 So you will see that the network address is 160.26.128. Okay. The 129.49 is the network address that's going to be somewhere in this range. But we take the mask, we look at what's the same in the IP address, and that will become the network address. Okay. Now we look for the broadcast address. The broadcast address will be found by taking everything in the host portion and making it into a 1. So if you look here at the binary that I've got at the bottom, this part is the same as the mask at the top. But everything to the right of the 17th digit has become 1. And what happens when everything becomes 1? We get 255.255, which is what the broadcast address is. It's 160.26.255.255. Lastly, after we've found out what the network address is and what the broadcast address is, we can see what the valid range of host addresses will be. So you cannot use a network address as a host address. It just doesn't work. But you can use the next digit up, which is 1. So the first host that could be on that range for subnetting is 160.26.128.1. And the last host address will be 255.254, because we cannot use a broadcast address as a host address. So there's 2 less than the full range of valid hosts. Okay, I hope that makes sense. It's a bit like if I draw a line with some bits on the end. Everything between those two bits at the end can be used, but the markers on the end cannot be used. Yeah, because they are the network address and broadcast address, respectively. Okay. Next slide. Another useful thing to know is about the number of valid hosts. So to calculate the number of valid hosts on a network, you need to use the formula 2 to the power n minus 2, and that's because of the reasoning I just told you. The minus 2 represents the network address and the broadcast address, so you can't have them as a valid host address. That's why we have to subtract the 2. And n is the number of zeros in the subnet mask. Number of subnets is going to be 2 to the power n, where n is the number of host bits that are borrowed. So this requires knowing whether the range is in a class A, B or C range. It will become clear as we look at the question that I'm going to come on to next, but this is the most important thing to know, that the number of hosts is 2 to the power n minus 2, where the minus 2 represents the network address and the broadcast address. So here we're going to look at variable length subnet masking, and this is the really difficult stuff, or it sounds difficult, but it's not really if you know what you're doing with it. So I'm going to go through the maths of variable length subnet masking, and then we'll look at why and how afterwards. So the requirement is take 192.0.0.0/24, so it's a class C subnet, and I want one subnet with 120 hosts, I want 3 subnets with 24 hosts, and I want 4 subnets with 2 hosts. So we're going to split this range, 192.0.0.0, to satisfy those 3 requirements. Here's the first one. So 192.0.0.0/24. The requirement is one subnet with 120 hosts. Okay, so the first thing we need to do is a host calculation, and that is with the formula 2 to the power n minus 2. 120 hosts means we're going to have to look at a number that's bigger than 120, and the number that's bigger than 120 that can cater for 120 hosts is 2 to the power 7, or 128. 128, subtract the broadcast and the network address, will give me 126. So 126 in a valid range is more than enough for the 120 hosts in that subnet. Okay. So the host portion of the mask will therefore have 7 zeros, because we're looking at 2 to the power 7, or 11111.11111.1.0000000. So we're looking at a /25 subnet mask. So the way of thinking about this is, if you're splitting it into 128, it's like splitting that final octet in half. Okay? The first address is 192.0.0.0. The broadcast ID will be 127, because that's the highest number you're going to get before you move on to the next subnet, which would be 128. Leaving you with 126 valid hosts in between. And then there would be a second subnet, 192.0.0.0.128, going all the way up to 255, with valid hosts 129 to 254. Now we don't actually need that second subnet. We don't need the 128 or 255 range. Why? Because the question says it's one subnet we need, not two, just the one. So this first subnet of 192.0.0.0 to 127 will be sufficient. Part B was 3 subnets and 24 hosts. Notice, by the way, I've started this range at 192.0.0.128. So I've excluded the first range of 000 to 127 because that's going to be used by the first requirement. This second requirement, 3 subnets and 24 hosts, again, host calculation, 2 to the power n minus 2. Well, 24 hosts is less than 32, and 32 is 2 to the power 5. I again have to subtract my network and broadcast IDs, giving me 30 hosts for each subnet. So the host portion will have 5 zeros because 2 to the power 5 is 32. And you can see here, those are your 5 zeros on the end. It's not letting me select it. There we go. All the rest is going to be ones, meaning we're going to have a /27 subnet mask. So we need to then split the range into those various different subnets. So we're starting at 128, which was the second subnet from the previous question, and we're going to go up in 32s after that. So add on a 32 to 128 gives me 160. Add on 32 to 160 gives me 192. Add on 32 to 192 gives me 224. So we've generated 1, 2, 3, 4 subnets there, which will have valid hosts between 129 and 158, 161 and 190, 193 and 222, and this final one, the valid hosts, I better put those in, are 225, not 255, 225 to 254. Now you're probably wondering why I didn't include those. Well, the question said 3 subnets, 24 hosts. So the first 3 between 128 and 159, 160 and 191, and 192 to 223 is sufficient. We're going to carry forward this 192.0.0.224, if I scroll this down, to the final part of the question. Okay. Good, let's move on to the next slide. And that is 4 subnets with 2 hosts per subnet. So again, we're going to do the host calculation, 2 to the power n minus 2. We're going to need 4 to generate 2 hosts because 2 squared is 4. 4 minus 2 will be 2 hosts for each subnet. 2 hosts means that there's only going to be 2 zeros in the subnet masks, meaning we're going to have a /30 here. So then we have to split the range up, and if I extend the page so you can see it a bit better, we start at 224 because that's where the last set of subnets ended, and going up in 4s will give me 228, 232 and 236. The broadcast address is going to be one less than 228, so it'd be 227, 231 and 235. And your valid hosts would be 225, 226, 229, 230, 233, 234, 237, 238. And that's it, because it's 4 subnets, we're going to need all 4 of those. So if you're still struggling to understand that, I've come up with a way of trying to make it straightforward. And I need to grab my arrow here to just shrink this down because it's a bit too big to the screen. So I would say imagine a cake, but it's probably a bit difficult to do. So we're going to imagine a line. Okay, that line is from 0 to 255. And remember the original question, it was 192.0.0.0/24. Okay, so the first part was one subnet with 120 hosts. We worked out that we needed 128 because 128 was sufficient for the 128 hosts. And we split that line from 0 to 128. So that will cope with the one subnet and the 120 hosts. And the valid host addresses will be 192.0.0.1 to 192.0.0.126. Okay, so that was the first part of the variable length subnet masking. We've split the line in half to cater for that requirement. The second part of it was 3 subnets with 24 hosts. So you can see here that I've gone up in 32s because 32 is the only number of hosts that will cater for 24 hosts in each subnet. So 128, 160, 192, 224, and those would be your valid hosts there displayed on the screen. Okay, 192.0.0.129 through 158, 161 through 190, and 193 through to 223. Lastly, and by no means least, I wonder if I can shrink this down. Let's try grouping everything. Yeah, well, that's better. It's in view now at least, which is good. So we have got, for the last part, 4 subnets and 2 hosts. It's really small there. Your network ID was 224 through to 227, broadcast ID, 228 to 231, 232 to 235, and 236 through to 239, with valid hosts as shown: 225 to 226, 229 to 230, 233 to 234, and 237 to 238. But do you see how it's been sliced, this range, into different segments? So the first segment was 128 block, the second segment was into 32 blocks, and then the last section is in blocks of 4 up to 240. So there's a part of the range there between 240 and 255 that is not used, which might be used for a different requirement later on, but in this particular case of us splitting the subnet into its various sections, it's not used between 240 and 255. So we're finally on to my final slide. A little bit about that last requirement, /30. It's called a point-to-point network because you're only going to have 2 hosts in it. So point-to-point makes sense, only 2 hosts. And something else that's interesting, variable length subnet masking can expand above and beyond a specified range if more subnets and hosts are required than the range can be spliced into. So for instance, that range of 192.0.0.0/24, we were able to fit all 3 requirements into that one range. However, if I needed more space, i.e., let's say the question said we want 3 subnets with 120 hosts, then you would have one subnet between 0 and 127. You'd have another subnet between 128 and 254. And then you'd have to go on to the next range, 193 to 193.127. So if you need more space, you do have to allocate more space to get that range in and done. And that's variable length subnet masking. Obviously, I can't go into more detail as to what that might be, because it is dependent on what the question actually asks for, how you split that range up. So it is practice. It's, can you do what the question's asking you to do, and can you display it in a very diagrammatic form to be able to, you know, show whoever's looking at the questions what's going on. But I think this really does explain it nicely as to what VLSM is all about. It's about splitting ranges into subnets, and those subnets will have a certain amount of hosts in each subnet, and users and devices will be on those subnets. Right, I am done on this topic of subnetting. I hope you've enjoyed my hour on binary conversions and subnet masking. It's well worth watching other videos and reading more on it, but this is the simplest I can make it on actually doing subnetting. So I hope that's been helpful to those of you who are watching and who've made it through to the end of the full hour. And I will leave you with it there. I'm going to end stream now, and maybe come back and do something else in a bit. But that is subnetting. Bye everyone. Hi everyone. This is a friendly reminder to like, subscribe and hit the bell notification icon to stay tuned for future videos on this channel. I also welcome constructive comments in the box below, and you can gain access to any of my teaching resources through the link above. If you'd like to support me through donation, you can either go to paypal.me/JonathanKipping or patreon.com/JonathanKipping. Stay tuned and look forward to future videos.